So here it looks like we are launching a mass. We know the mass, we know the spring constant. We're using the spring to launch the mass up this ramp. Launches it into the air towards this tabletop, and it reaches the top of the table, but still in motion at 10 meters per second, presumably 10 meters per second straight forward. And we want to know how far did the spring have to be compressed in order to make that happen. So in a situation like that, I think it's best to start by choosing some initial and final instance in time. What do you think would be good places or times to call initial and final here, based on what we're trying to find in part A? Is there some early instant in time and some later instant in time where we know everything about one of those instants and we're trying to find something about the other instant? Zero what? Like not numbers, but locations. What would be some good locations or situations to describe as initial and final here? If what we want to know is how far was the spring compressed in order to be able to reach the top of the table at this speed, what would be a good beginning and end of the interval? Yeah, spring, well, I would say compressed rather than stretched out. And when we're talking about initial and final, we're not really just looking for a number. We're looking for a description of a situation. So how would you describe the initial situation? What's going on with the location of the block, the state of the spring, stuff like that, and what's going on in the final situation? I'm not sure. Somebody sent it to me on Discord. But in part A, if we're just talking about the block being launched, what's the beginning of that launch and what's the end of that launch as far as what we're considering is concerned? Because if we want to apply the conservation of energy stuff, we've got to be able to have an initial and final instant to consider. So if we're launching this up to the tabletop, what's the beginning and end of the time interval we're considering? What would be a good starting point and ending point for this time interval that we're considering here? If you wanted to physically set up this experiment, how would you describe to somebody how you're setting up the beginning? And how would you describe how you know you're done with the experiment? Distance of what? Well, we're not trying to figure out what's going on when the block reaches equilibrium. What is this question part A actually asking? Part A is describing an interval of time. It's describing a process. What's the end of that process? Yeah, I would say when it lands on the table, because the part A gives us some information about what happens when the block reaches the top of the table. That instant when it reaches the top of the table is a known quantity. We know that at this instant, it's reached a known height and has a known speed. So we know the speed and the height when it reaches that location. I would say that's a good time to use as the final instant in time. So let's describe that as final. In the final situation can be described by the block has just reached the tabletop. And we know its height at that instant in time, I guess we can call that Y final, is 3 meters off the ground. And we know the speed at that instant in time is 10 meters per second. So we know what's going on at that instant in time. The file is literally just this picture. So if you want, you could take a screenshot of it directly from the video chat. What would be a good instant in time to use as initial? What's another point in time somewhere in this interval we're talking about that includes some information we're trying to figure out? Yeah, I think that'd be a good time to use as initial if the spring is compressed and at rest, because we know that what we're trying to find here is how far was the spring compressed. If we're compressing the spring and then letting go, that instant when we let go has some information we know and some information we don't, specifically some information we're trying to find. So that I think that would be a good initial instant to use. The block has just been released from the spring, from the compressed spring. In that case, we can say the initial height, what's the initial height at the instant we let go here? At the instant we let go of the block, what's its height? Yeah, I'd call that 0 because it's at ground level. And we'll also need an initial speed. At the instant you let go, what's its speed? Looks like we're just releasing it from rest. So yeah, that would also be 0. So this block starts off at ground level at rest. but it's being launched by this spring. The spring is able to launch it because it has some initial compression, which we could call X initial. And we don't know what that is yet. We're trying to find how far was the spring initially compressed. So we could say X initial, the initial compression of the spring, like how far it was displaced from equilibrium, is an unknown. But we do know by the time the block reaches the tabletop, what's the compression of the spring? How would you describe the spring at the instant the block reaches the tabletop? The speed is 10 meters per second, so we've got V final. But how would you describe the state of the spring at the instant the block reaches the top of the table? We compress the spring with the block on it, then we let go. The spring pushes the block. What's the final situation for the spring itself? Yeah, the spring is going to eventually be at equilibrium because the spring pushes on the block and pushes and pushes. By the time the block leaves the spring is now back to equilibrium. So the spring's final displacement is no displacement at all. It's back at equilibrium. For Y initial, where does the block start off in terms of height in the initial situation? At the beginning, in the initial situation, how would you describe where the block is? Yeah, the block is at ground level. And we get to choose a coordinate system here. We can call Y equals 0 wherever we want. I think it would probably be most convenient to call ground level Y equals 0. So let's call this location on the diagram Y equals 0. And then the tabletop would be how high? Relative to that. Yeah, that'd be Y equals 3 because it's 3 meters above the location we're calling 0. And this is not the only coordinate system we could use here. We could use other coordinate systems. For instance, we could call the tabletop Y equals 0, and then the ground being below that would be Y equals -3. So, or you could call ground level Y equals 100, and then the tabletop would be Y equals 103. It doesn't really matter what you call these Y values. The important thing is the difference between them. So just choose some elevation to call Y equals 0, and then measure everything else relative to that. Usually it makes the most sense conceptually to call ground level Y equals 0, but you don't have to. There's no reason, there's nothing special about 0 here. But it looks like we now have initial and final values for everything except for X initial. That's still missing. But since we have everything else, we should be able to set up an equation and solve for X initial. Any questions on that so far? So during this period of time, what types of energy are changing? If we've got a change in height, a change in speed, and a change in spring potential or spring displacement. Yeah, we've got a kinetic energy related to the change in speed. We've got gravitational potential energy related to the change in height. And we've also got spring potential energy related to the change in the spring's displacement. So if we write those out, delta kinetic energy plus delta potential energy of gravity plus delta potential energy of the spring, assuming this is a closed system, because it says friction and air resistance are negligible, we can assume that those changes add up to 0. And if we fill in formulas for those, kinetic energy, the change would be half the mass times change in squared speed. Potential energy of gravity mass times gravity times change in height. And spring potential energy, half the spring constant times change in squared displacement. So that should work as our conservation of energy equation here. Any questions on that equation setup so far? Potential energy of the spring. And that's correlated with the change in how compressed the spring is. The potential energy of the spring is how much energy the spring is storing based on how much it's been displaced from equilibrium. And that's whether it's stretched or compressed. If you take a spring and stretch it, you're storing energy in it. If you take a spring and compress it, you're also storing energy in it. So it doesn't really matter whether it's stretched or compressed. That corresponds to the idea that x is being squared here. So it doesn't matter whether x is positive or negative. All that matters is it getting closer to equilibrium or further from equilibrium? In fact, we could even take a look at the positive or negative signs of each of these. Is the speed increasing or decreasing from start to finish? Yeah, we've gone from 0 meters per second to 10 meters per second. So the speed has increased. So this would be a positive change. And has the height increased or decreased? Yeah, we're going from y equals 0 meters, the ground, up to y equals 3 meters, the tabletop. So delta y is also positive because height is increasing. And what about the spring? Is the spring getting closer to equilibrium or further from equilibrium? Yeah, it's getting closer to equilibrium, so that's a decrease in spring potential energy. In general, getting closer towards equilibrium is decreasing energy. Getting further from equilibrium is increasing energy. And so we have two positives and a negative adding up to 0. Presumably, we've got a very large negative and two more moderately sized positives canceling each other out. And that doesn't influence how we write out the equation. It's still this change plus this change plus this change. It's just good to keep in mind which one of these changes are going to be positive values and which ones are going to be negative values in terms of the actual value, the actual numerical results. Any other questions on that setup so far? The v squared is part of the formula for kinetic energy. In general, kinetic energy, translational kinetic energy is half the mass times the speed squared. If we apply a delta to that, that's the final half the mass times speed squared minus the initial half the mass times speed squared. So final kinetic energy minus initial kinetic energy. But if you factor the m/2 out of both of those, because it's the same mass in both of those terms, you get m/2 times v final squared minus v initial squared. In other words, half the mass times the change in squared speed. So that's our usual formula for change in kinetic energy. Half the mass of the object times the change in squared speed. And I always put the v squared in parentheses there, and then the delta outside the parentheses to signify you're squaring the initial speed and squaring the final speed separately, and then taking the difference. So that's what we mean by delta speed squared. Any questions on that so far? All right, then let's try filling in those deltas. If we expand each of those deltas, each one of these can be written as final minus initial. So half the mass times final speed squared minus initial speed squared. And likewise, the height, delta height, can be written as y final minus y initial. And delta x squared can be written as x final squared minus x initial squared. And of those, what's the only unknown? What's the only part of this we don't have a value for? Yeah, that's really what we're trying to find here, right? We want to know how much has the spring initially been compressed? What was the initial compression of the spring? So we can algebraically solve for that. And you could plug in all the numbers now and then solve for x initial. I usually find it more useful to isolate the variable in terms of all the other variables and then fill in the numbers at the very end, for a variety of reasons. Partly because it makes it less likely to make calculation errors if you're doing all the calculations in one step at the end. And also, if you solve it in terms of variables, then instead of just getting a number, you get a formula no matter what the variables, no matter what the values are. So that's often useful if you're going to be running the same sort of analysis to several similar situations. If you can set it up in terms of variables and just solve it once, that can save a lot of trouble. However, there are some values that are zero, and zeros are often much easier to work with if you actually fill them in, because you don't really need to do any calculation, it's just zero. So let's fill in the values that are zero, because those are just going to be gone anyway. For instance, we know that y initial is zero. We know that initial speed is zero. We don't know the initial displacement of the spring, but we know the final displacement of the spring is zero. So that makes a lot of these terms much simpler to work with. Also, I'm noticing that a couple of these have a divided by 2 in them. Let's get rid of that by multiplying both sides by 2. So if we multiply both sides of the equation by 2, let's see, and fill in the zeros, let's see what's left. We got mass, because the 2 cancels out, times v final squared minus 0 squared. So that's just v final squared. Plus, we're multiplying by 2, so 2mg times y final minus 0 is just y final. Plus k over 2, but we're multiplying by 2, so k times 0 minus x initial squared becomes negative x initial squared. All adds up to 0. We could also pull out that negative and write this as minus k times x initial squared. So that gives us a much simpler equation that's still written in terms of these unknown variables. We're just filling in the values we know are 0. And I think that's going to make it much easier to solve for x initial. In fact, what would be our next step here if we wanted to isolate x initial? Algebraically, how would you start isolating x initial here? Yeah, we could subtract these other 2 terms to the other side, or possibly more easily, we could just add kx initial squared to both sides. I think that's going to make the next few steps easier as well. So let's just add k times x initial squared to both sides. That'll have the same effect, but possibly save some time later. So that gives us, moving up to a new line, mass times v final squared plus 2mg y final equals k times x initial squared. And then what else do we still need to do to solve for x initial? What would be our last couple of steps to isolate x initial here? Yeah, divide both sides by k. So we get m over k times v final squared plus 2mg over k times y final equals x initial squared. And yeah, then take the square root of both sides. So that gives us a formula, not just a single number, but a formula for how much the spring needs to be compressed. Any questions on that so far? And this can also be useful, is a formula like this can be useful for giving us an idea of how each of these values influences the initial compression we need. Like for instance, larger V final or larger Y final would lead to a larger X initial, which means the higher we want it to go and the faster we want it to be going when it gets there, the more we'll need to compress the spring. Also, larger M will lead to a larger value for X initial. So the more massive the object is, the more we need to compress the spring. Whereas a larger K value, since K is in the denominator, larger K value leads to a smaller result. In other words, the stronger the spring is, the less we need to compress it to get this same result. Any other questions on that so far? And at this point, I think we can fill in some values here. X initial equals square root of, also before we do this, let's factor out M and K, because I notice both of these terms have M and K in them. So M over K times V final squared plus 2G times Y final. That way we just need to calculate M over K once. So filling in those values, what is M over K going to look like? If we've got 0.4 kilograms divided by 400 newtons per meter, how could we simplify that? In general, a very useful technique if you're dealing with multiplication or division of inconveniently large or inconveniently small numbers is to write everything in scientific notation. Like 0.4 is just 4 times 10 to the negative 1. And 400 is 4 times 10 to the 2. If you divide 4 times 10 to the negative 1 divided by 4 times 10 to the 2, what's going to happen? What would happen if you divide those? 4 times 10 to the negative 1 divided by 4 times 10 to the positive 2. What's 4 divided by 4? And why is that? What's happening with these values that leads to that result? If you have 4 in the numerator and 4 in the denominator, what happens to that? And yeah, those are going to cancel out. 4 divided by 4 is 1. And then the rest of it, we've got 10 to the negative 1 divided by 10 to the 2. What can you do with exponents when you're dividing? If you got 10 to some power divided by 10 to some other power, what can you do with those exponents? Yeah, we can subtract the exponents. 10 to the negative 1 divided by 10 to the negative 2 equals 10 to the negative 1 minus 2, which is negative 3. So this whole thing for the mass over the spring constant reduces to 10 to the negative 3. We should also keep track of the units. Looks like we've got kilograms divided by newtons per meter. Dividing by newtons per meter is the same as multiplying by meters per newton. So kilogram meters per newton. So that's the m over k multiplier here. Mass over spring constant is 10 to the negative 3rd kilogram meters per newton. Right, what? The units? Yeah, I mean, it's not really a conversion. It's just the idea that kilograms, if you're dividing by a fraction, that's the same as multiplying by the reciprocal. Dividing by newtons per meter is the same as multiplying by meters per newton. So you get kilograms times meters in the numerator and newtons in the denominator. We could do another conversion here by replacing newtons with what it means. Anyone happen to know what newton stands for? In terms of the base units, kilograms, meters, and seconds. You're going to see this in more detail in 7b, but for now, what you need to know is that newtons is the same as kilograms times meters per second squared. That's ultimately from a mass times an acceleration. Kilograms is mass, meters per second squared is acceleration. We'll see that in more detail in 7b when we get to the study of motion. But in general, anytime you see newtons, you can immediately replace that with kilograms meters over second squared. In fact, if we do that here, dividing by kilogram meters per second squared, that's effectively 1 over newtons. So that's going to be the same as the reciprocal of that, second squared over kilograms times meters. So dividing by newtons is the same as multiplying by second squared over kilogram meters. So we're left with kilograms meters times 1 over newtons, which is second squared over kilogram meters. And what does that simplify to? If we've got kilograms times meters divided by newtons, and we fill in newtons as kilogram meters per second squared, what happens when we simplify this? If we have kilograms times meters times second squared divided by kilograms times meters, what's going to happen? Does anything simplify there? What's going to cancel out here? Or what are the remaining units? Does anything cancel out? Looks like we have kilograms and meters in the numerator and also kilograms and meters in the denominator. So kilograms divided by kilograms is 1, and meters divided by meters is 1. So it looks like all that's left is seconds squared. All this stuff with kilograms divided by newtons per meter, that whole thing just works out to seconds squared. So this multiplier here, mass over spring constant, is really just 10 to the negative third square seconds. And a second squared on its own doesn't really have much meaning. Like if it was meters squared, that would be area, or meters cubed would be volume. Second squared, there's not really an area of time. But second squared is just what the units work out to, and that's going to interact with the units of everything else. So filling that in, we get square root of 10 to the negative third second squared. That's our meter or mass over spring constant, times, and then V final squared. Do we know what the final speed is? What's the final speed we want this to have when it reaches the tabletop? What value can we use for V final here? Yeah, we know V final needs to be 10 meters per second. If we square that, what do we get? 100, and then what will the units be? Keep in mind, we're applying the squared to the whole thing, including the 10 and the units. So 10 squared, if we got 10 meters per second times 10 meters per second, the 10 times 10 becomes 100. Meters per second times meters per second becomes meters squared over second squared. So that's our units for velocity final squared, 100 meters squared per second squared. Plus, and then we also have 2 times mass times gravity divided by spring constant. Sorry, next one. 2 times gravity times y final. What's gravity and what's y final? Yeah, y final is 3 meters. And what are we using for acceleration of gravity here? What's the value of acceleration of gravity if you're on Earth? Yeah, closer to 9.8, but we'll round it off to 10 so we can do this in our heads. So 2 times 10 times 3 would be 60. And we need units for that as well. Y final is meters. Acceleration of gravity on Earth, acceleration of gravity is 9.8 meters per second squared. I think it's 9.81 meters per second squared. And that's really just describing the rate at which a falling object will accelerate. If you just got an object in free fall with gravity being the only force acting on it, it's going to get faster and faster and faster. The 9.81 meters per second squared is the acceleration, how fast it's getting faster. However, in problems like this, we often round it off to 10 if we're just doing a quick mental estimate. If you're going to be using a calculator anyway, you would use 9.81. But if you're just estimating it, we usually round it off to 10. Yeah, this is we're on Earth, and most of the problems we're going to be doing are on Earth. So I would recommend committing this to memory, because this will always be the acceleration of gravity when you're on Earth. Other planets will have a different value for g, but on Earth, it's 9.81 meters per second squared, or as a quick estimate, round off to 10. So if we round this off to 10, we got 2 times gravity. So 2 times 10 is 20, times y final is 3, so 20 times 3 would be 60. And as for the units, gravity is in meters per second squared, y final is in meters. The meters combined, so we get meters squared per second squared. So I think that does it for all the numbers we need to plug in. Any other questions on that so far? Then we could combine the 100 plus the 60 to get, let's see, 10 to the negative 3 second squared times, that just becomes 160 meters squared per second squared. Multiply those, we get 160 times 10 to the negative 3rd. And what happens to the units of measurement there? If we're multiplying second squared times meters squared per second squared, what do we get? Yeah, that'll be meters squared. So x initial is going to be square root of 10 to the negative 3rd is just going to shift the decimal point 3 spaces over. So that'll be 0.16. And then our units are meters squared, since the second squared cancel out. So square root of 0.16, that might actually be easier to write as a fraction. If we write that as 16 over 100, square root of 16 is 4, square root of 100 is 10. So we just get 4 over 10. And then square root of meters squared would be meters. So 4/10 of a meter, or 40 centimeters. That would tell us we need to compress the spring 40 centimeters in order to make this happen. Any questions on that? So overall, some general recommendations. Whenever possible, include units of measurement in all your calculations. Like when you fill in, let's say 3 meters for y final, don't just write it as 3, actually write it as 3 meters. Include the units in all the calculations as you're filling in values. It's useful for, first of all, for making sure that all of the units match up, because if they don't, you'll know you have to do conversions. And also figuring out what the final units of measurement are. Like here we got meters as a distance. That makes sense. Meters, our distance should be measured in meters. If we had gotten like seconds times kilograms as a result, that would suggest that something's gone wrong somewhere. So always include units when you're running the calculations with the actual numbers. Before you plug in the numbers though, I would recommend whenever possible, solve in terms of the variables first to get a formula for the result and then fill in the numbers. Ideally, you should be able to get it to the point where you do all the calculations on one final line at the end. If you're doing it on a calculator, this means that you should only need to press the equals button on your calculator once in the very last step. What else? Oh, and one other thing I wanted to mention, there's a lot of quantities that go with certain substances or certain planets that we use all the time, like G for 9.81. Or 9.81 for G on Earth. Anything that's a property of the Earth or anything that's a property of water, I would say would be very good numbers to just memorize, because we're working on Earth and working with water all the time. So, I mean, it's certainly possible to look up those numbers, but it's good to have them on instant recall just because they show up so often. The calculator part, yeah, I was saying that if you set it up and if you set up your equations so that you solve in terms of the variables and then fill in the numbers at the very end, then if you're using a calculator for this, you should only need to press equals on your calculator once. You could type in this entire line. Let me box in what I'm talking about. This entire line without the units of measurement, just the raw numbers. You can type this into your calculator with the properly placed parentheses and then just hit enter or equals once. Yeah, if you're using a scientific calculator, as long as it has buttons for parentheses, then this should be possible. You just type in the square root button and then carefully using parentheses 10 to the negative 3 times in parentheses 100 plus 60. If you know how to use the parentheses button on your calculator, then you should be able to just type this all in one line and press enter or equals once. And that should do it. And that also reduces error, because if you type in a certain calculation and then write down the result and then type that back into the calculator, round it off, and then write down the result, and then type that into the calculator, round it off, and write down the result, every step where you're rounding something off introduces more and more error to the result. Whereas if you type it all in one line, then the calculator preserves as much accuracy as it can and spits out the final answer as accurately as it can. So it reduces the amount of error you're accumulating step by step if you do all the calculations in one go at the very end. All right, I've got to get ready for a meeting, but let me know if you have any other questions for next time, and I will see you then.